This video is going to cover section 8.1 for UMA statistics, distribution of the sample mean. So a sampling distribution is when you list all possible values of a statistic from a sample listed. So one example is if we do the sample mean. So remember our sample mean's X bar. And if we were making a sampling distribution of the sample mean, we would list all possible means, sample size, n, whatever that is. So let's look at this one here. Let's say this was our population. Mary has 6 siblings. Sue has 2 siblings. Fred has 1 sibling. Joe has 2 siblings. So we're going to treat that as the population and find the population mean. So population mean is 6 plus 2 plus 1 plus 2 divided by 4 gives us 2.75. So that is our population mean. Now let's list all the possible samples of each size. So for n equals 2, we have Mary and Sue, Mary and Fred, Mary and Joe, Sue and Fred, Sue and Joe, Fred and Joe. So we have 6 different samples in there. Then if I did the same thing for the groups of 3, we'd have Mary, Sue and Fred, Mary, Sue and Joe, Mary, Fred and Joe, Sue, Fred and Joe. Those are all there. Now we're going to compute and record all of the sample means for each of those samples. So let's see. Mary is 6, Sue is 2, 6 plus 2 is 8, divided by 2 is 4. Mary is 6, Fred is 1, 6 plus 1 is 7, divided by 2 is 3.5. Mary and Joe would be 6 plus 2 again. And then Sue and Fred would be 2 plus 1, which is 3. Divided by 2 is 1.5. And then Sue and Joe would be 2 and 2. And Fred and Joe would be 1 and 2. What even is, I don't know, that A thing. I'm just going to ignore it. Sorry. Okay, and then Fred and Joe would be 1 and 2. Which is 1.5. You do that for the sample size 3. Pause the video and come back and check. So Mary, Sue, and Fred. Mary, Sue, and Joe. Mary, Fred, and Joe. And then Sue, Fred, and Joe. So now we have all the sample means listed. So we're going to turn those into a probability distribution of the mean. There we go. So in order to do that, we're going to list all of our possible means. So we had 1.5, 2, 3.5, and 4. Out of our 6 groups, 2 of them had 1.5. So 2/6, which is 1/3, which is 0.33. Out of those same 6, only 1 had 2, so 1 out of 6, which is 0.17. Only 1 had 3.5, and 2 had a 4. So there's our distribution. Now we're going to find the sample mean. So it's the weighted mean, where you do your amount times your probability, add them all up, or you can put them in your calculator. So let's pull up our graphing calculator here. I'm going to hit stat. Sorry, I'm just going to clear that. So stat, edit, and in L1, I'm going to type the values. And then in L2, I'm going to type the probabilities. Okay. And then we do stat, arrow over to calc, our one variable stats, making sure our frequency list is 2. That's how we did our weighted mean. And then if we go up here, the sample mean is 2.75. So you go ahead and do that for the other one. Pause the video and check and see how you did. And if we put it in our table, and we get 2.75. So what does this show us? Well, it shows us that the sampling distribution of the mean, when we list all of our possible sample means, the average of that is always going to be the same as our population mean. So this is showing us that we can use a sample and the mean is going to stay the same, so we don't have to worry about that changing with our sample. So let's look. IQs are normally distributed with a mean of 100 and a standard deviation of 15. So this is the world. This is the population. And then we want to know the sampling distribution of the sample mean, n equals 9. So if we did that, we'd see all of the possible distributions of 9 people. So if we did a simulation, we get a whole bunch of populations of 9, and the mean is not going to change. It's going to be 100 no matter what. What changes is the standard deviation. The bigger n gets, the smaller the standard deviation gets. So n equals 9 is going to have a bigger standard deviation than n equals 100, which is going to have a bigger standard deviation than n equals 1,000. So in order to take advantage of this and acknowledge it, we use what's called the standard error of the mean when we're finding the sample deviation. And that takes the deviation and divides it by the square root of n. That just acknowledges that the bigger n gets, we're changing our standard deviation. So we already know mean and standard deviation of those symbols. These symbols here with the sub x bar, so written out, it would look x or mean sub x bar, standard deviation sub x bar. That's saying, hey, we know we did a sampling distribution of the mean. We just proved the mean stays the same. And then because of the way the standard deviation changes, that's where we use the standard error of the mean. Now your hint on your tests and such are going to be, you'll have a question that says, what is the standard error of the mean? And then the next couple, you're going to use it. In reality, it's when you're given the population information and then asked about the probability of a sample. When you have both things, that's when you use the standard error. So let's do one. The IQ of humans is normal with mean 100 and standard deviation 15. Compute the probability of a sample size 10 gets a mean greater than 110. So whenever we're doing probabilities, we're now norm CDF. Our lower is going to be 110. Our upper is going to be 1E99. And now we're going to use those from above, the mean sub x bar. So the mean does not change. That's still 100. And then we use the standard error. So we're going to do 15 over the square root of 10. So that's acknowledging that we're going from a sample to a population. And then we put that in the calculator. So second vars, norm CDF, 110, 1E99, 100, and then 15 divided by square root 10. Square root 10. And we get 0.0175. So that is the probability, 1.75%, that in a sample of 10 people, the mean would be greater than 110. The central limit theorem helps us when our population's not normal. What it tells us is that regardless of the population shape, we don't care what the population shape is. Regardless. Oops. The sampling distribution, so the distribution of the sample mean is normal. So because we're doing the distribution of samples, it becomes normal and symmetrical. That's why we can use norm CDF. So let's look at this. The mean weight gain during pregnancy is 30 pounds, with a standard deviation of 12.9 pounds. Rate gain during pregnancy is skewed right. An obstetrician obtains a random sample of 35 low-income patients and determines their mean was 36.2. Does this suggest anything unusual? So when we're doing unusual, that's going to be our greater than. So greater than or equal to 36.2 is what we're trying to solve for. Now our population mean is 30, and our population standard deviation is 12.9. And now we're doing a sample. So our sample mean stays the same. Deviation, we now do the standard error of the mean and divide by the square root of n. Now we can do our norm CDF. Not sure why the colors change, but it is what it is. So our lower is 36.2. Our upper is 1E99. Our mean is 30. And our standard deviation is 12.9 over root 35. Put that in a calculator. Norm CDF. Divided by square root 35. And that gives us 0.002. So 0.22%. Then we ask, does this suggest anything unusual? So 0.0022 is less than 0.05. So this suggests unusual. So as soon as it's less than 0.5, we're unusual. Then what we're saying is what could have caused this? This just wants you to come up with some ideas. So if you think about it, at the grocery store, healthy food costs way more than unhealthy food. So if you're a low-income person, it's harder to afford maybe the healthy food. So maybe that's why you gain more weight. There's one example. It could be they got a bad sample and their sample all happened to gain more weight. It's hard to say, but the point of this is just having something that makes sense. So that is 8.1. Let me know if you have any questions.